Hey everyone! So, what if our most successful theory in all of science isn't really a theory of reality at all? What if it's just a perfect recipe for calculating shadows on a wall? That's the idea we're going to explore today. A really fascinating and surprisingly ancient way to wrap our heads around the weirdness of quantum mechanics. Let's get right into it.
So this is the big puzzle, right? The thing that keeps physicists, and probably a few philosophers, up at night. On one hand, quantum mechanics just works. I mean, its predictions are unbelievably accurate. But on the other hand, what it seems to tell us about reality itself, it's just, well, it's weird. It feels totally counterintuitive to everything you and I experience in our normal lives.
And when I say successful, I'm not kidding. We're talking over 100 years of testing this thing over and over, and it has never made a wrong prediction. Not once. I mean, think about it. Lasers, the microchips in your phone, MRI machines, our entire modern world is basically built on the back of this theory. It is an absolute powerhouse.
Okay, so how do we even begin to make sense of all this weirdness? Well, here's a thought. What if the key isn't buried in some high-tech physics lab, but in an idea from over 2,000 years ago? Yeah, we're going to take a quick trip back to ancient Greece.
So you've probably heard of this. It's Plato's famous allegory of the cave. Just imagine this scene. You've got these prisoners who have been chained up their whole lives inside a cave. All they can do is stare at a blank wall right in front of them. That wall, that's their entire world. It's the only thing they've ever known.
Okay, so behind the prisoners, there's a big fire burning, and people are walking back and forth in front of that fire, carrying all sorts of things. And what happens? Well, the fire casts shadows of those objects onto the wall, the same wall the prisoners are staring at.
And here's the kicker. For those prisoners, those flickering shadows on the wall, they aren't just shadows. To them, they are reality. It's all they've ever seen. They'd probably give them names, study their patterns, maybe even try to predict where they'll go next. And all the while, they have no idea at all about the real three-dimensional objects casting them. Just hold on to that image, okay? It's super important.
All right, let's fast forward back to today, because this ancient story, it gives us this incredible new way of looking at quantum mechanics. It's time to connect Plato's cave to the quantum world.
And this is where it all clicks. The analogy maps onto quantum mechanics almost perfectly. You see, the shadows on the wall, those are like the results we get from a quantum measurement. You know, that definitive click from a Geiger counter, a flash on a screen, a single data point. The wall itself, that's the act of measurement. And the real object that's casting the shadow, well, that's the mysterious, unknowable quantum state itself, the thing we can never, ever see directly.
Now, this is a really important point. This quantum wall isn't a physical place, it's an event. It's that specific moment when a quantum system interacts with one of our measurement devices. You know, a piece of equipment that lives in our big, clunky, classical world. It's the boundary line, the exact point where the fuzzy, unobserved quantum world becomes a concrete, observed fact.
And this right here is what quantum mechanics is so incredibly good at. It doesn't even try to describe the real object behind the scenes before we look. Instead, what it does is give us a perfect mathematical rulebook, a kind of calculus, for predicting the chances of seeing all the different shadows that could possibly appear on that wall.
So this leads us to a pretty deep idea. Maybe all the weirdness we feel about quantum mechanics comes from us, from asking the theory questions it was never, ever meant to answer. It turns out that what the theory doesn't say is just as important as what it does say.
Think about it. The math, the core engine of quantum mechanics, works flawlessly without ever having to say what a particle is doing before we measure it. The theory is just silent on what reality is like before we look. Now, this is a huge deal, because other interpretations really try to fill in that gap, right? You get ideas like many worlds or that consciousness plays a role. But in this view, that silence isn't a bug, it's a feature. It's a fundamental part of the theory's design.
Let's just sit with this quote for a second. Ontology sounds fancy, but it's just a term for the study of what really exists, of being. And this quote, it just nails the whole idea. It's saying a theory can be totally complete when it comes to predictions, but at the same time be totally incomplete when it comes to telling you what is. Two different things.
Okay, so if it's not a theory of reality, then what in the world is it? Let's try to put all these pieces together and reframe what quantum mechanics is actually all about.
You know, when you break it down, the logic here is actually super simple. Step 1, the theory's math is all about one thing, the act of measurement, which physicists call a projection. Step 2,
every single prediction we can possibly make comes directly from these projections. So what's the conclusion? The theory is describing the projections themselves, the shadows, not the thing that's being projected.
And here's the really cool part. This isn't just some neat philosophical metaphor. No way. In this super advanced field of quantum information science, physicists actually use the term classical shadows. It's what they call the regular, readable data that they pull out of a quantum system. So the language of the science itself is pointing us right in this direction. How cool is that?
So, this brings us back to the big, provocative question. What if we've spent the last 100 years being so confused simply because we've been asking the theory to be something it never was? What if we've been pulling our hair out trying to understand the object when the theory was only ever designed to tell us about the shadow?
This is really the key thing to take away from all this. Just because you have a flawless system for predicting where shadows will land on a wall, that does not automatically mean your system knows anything about the real 3D object that's casting them.
And maybe, just maybe, that's the real answer to the quantum puzzle. Quantum mechanics might already be a perfectly complete theory, but it's a complete theory of the shadows, of what we can know, of what we can measure. It might be designed to be permanently and intentionally silent about the reality that casts them. Definitely something to chew on. Thanks for watching.